Hello to you. My name is Jessie Johnson. This is Flat Earth, Globe Earth, Perception, Perspective. There are differences. This is part 2. Part 1 is paragraphs 1 through 8 were read. In part 2 here, paragraphs 9 through 15 shall be read. We'll start with paragraph 8 as a form of continuity. Please watch all 3 parts 1, 2, and 3 for completion, and watch each part at least 2 to 3 times. And stop the video at any point you wish in order to write down things and in order to absorb the information. Number 9. We'll start with number 8 as a form of continuity. To see beyond the limit of the eyes, binoculars, cameras, and telescopes, you must go higher in altitude. Why? The higher one goes, the more one sees an expanded, broader view. On a flat plane, as you go up, the surface recedes, but not its view nor horizon. The surface lets you see more up to the next perception limit. That limit is equal to your height or altitude at each point above sea level, and the further the distance of the horizon from you. So the horizon rises with eye level. This is easy to check. Go into an airplane at 35,000 to 40,000 feet up. Look straight out of the window at 90 degrees. Not down, not up, straight out. The horizon will be equal to your eye level and the camera level. The pilot sees the same things. Paragraph 9. From 1 inch to 100 miles above sea level, the same thing happens. The horizon rises with eye level and camera level. Climb a tree at 30 feet, climb a hill at 100 feet, climb a building at 500 feet, get in a helicopter at 15,000 feet, climb a mountain at 20,000 feet, get in a plane at 5 to 7 miles up, get in a spy jet at 14 miles up, get in a balloon at 22 miles up, get in a rocket at 20 to 245 miles up. The same happens in each case. The horizon rises with eye level. Why? This is called distance to horizon altitude ratio. It is a form of field of view compensation on a flat plane. Field of view of the horizon stays at all points of altitude until the end of the platform is reached. Then height to horizon compensation stops. One starts to see the end of the platform and the physical fall of the horizon. We'll go to paragraph 10. There's a perception and perspective limit to all things on the ground and any height above the ground. This is why even the sun cannot be brought back into view on the ground while looking through a telescope, though it's revolving above a flat surface. The height above sea level produces perceptual and perspective limits. You must go higher. While in a plane at 37,000 feet up, you look down to see the ground, but never the horizon on a flat earth. This is easy to check. Simply get into a plane. On a curved surface, you must look down to see the horizon. On a large ball, you must look down. This is what would happen, but it would not happen on a flat surface. Please look at this picture. Now, the person who took this picture is on top of one of these mountains. All the way around here is standing on one of these top of these mountains. Here, this is a triangle. See this triangle right here? This is A at the beach, at the water level is A. Right here is the horizon. Right here at the horizon of the trees, right above this mountain point right here. If a person was standing here taking this picture, he or she would see this horizon along the line of sight. Along that line of sight, they would see this horizon at B. Now, draw a line from A to B. Then draw a line from B to C, which is the line of sight to the horizon. C is at the horizon point itself. And now, draw a line from A to C. This creates a right angle triangle. This is basic basic trigonometry. Very basic trigonometry. A, B, C, line of sight. This A to C creates a plane of inclination. A plane of inclination. See this long line straight at the bottom here? This is how much of the surface, more of the surface you would see at approximately maybe 200 feet above it. This is how much you would see. much of more of the surface you would see. You could not see this 200 to 250 feet of a plain nor surface if you're down at the beach. All you would see is across this line at the beach. Now let's continue. Look at this picture here. This illustration here. Let's start with A. Let's start with A. If you're 75 miles in altitude in a rocket, here's your rocket, you're 75 miles in altitude, 396,000 feet above the ground, you're above a flat plane, therefore your line of view, your line of sight, your line of sight is equal to 90 degrees to the altitude line, creating parallel lines. Now, if you're 75 miles altitude in a rocket, you're parallel to the ground on a flat earth. If you're 500 miles altitude on a large enough flat surface, the horizon will stay at eye level. There are 5 reasons for this. You and the ground, one of the reasons at least, is you and the ground are parallel. I'll give you the other 4 in a little while, but not on a ball-shaped surface. It is the height above sea level divided into the distance of the horizon from you, which is a ratio fraction. You would be 75 miles up, parallel to the ground for tens of thousands of miles. The horizon will stay at the point of eye level throughout for about 5 different reasons. The altitude divided into the distance to the horizon is a fraction. This produces a perspective vantage point, such as in C, right here, C. A perspective vantage point, though you are parallel, you have parallel lines above, even though your line of sight is parallel to the surface. Let's continue. In B, let's go to B, right here. You have a landscape or seascape that have appearance of being slanted upward from your position above the ground to the horizon. In other words, if you are 35,000 feet in B right here, 35,000 feet, the ground is still parallel to your line of sight. Here's your line of sight. Even though your line of sight and the ground is parallel, if you are 35,000 feet, because the horizon is so very far away from you, that because the line of sight is so far, the horizon is so far away from you, and the plane of inclination will make the horizon seem as though it's right along with your eyesight. It's plane of inclination. Let's go to C, please. Now, and this makes it seeming right angle triangle. It makes a seeming right angle triangle. This is basic trigonometry. Now, let's go to C. You have a perspective limit where the height and the height, land, water, and air meets at a point, even though the surfaces are parallel. These not surfaces, but your line of sight is parallel to the ground itself. Is still in fact parallel, but because you are 2,300, because if you're 100 miles above ground, you're about 2,300 miles away from the horizon. That means you have an altitude to distance of the horizon ratio limit, which creates a perspective vantage point. And let's continue. Now, this is the height altitude distance to the horizon ratio. Once again, in other words, your 100 miles altitude this is the height altitude to distance of the horizon ratio. In other words, your 100 miles altitude and the distance to the horizon is 2,300 miles. 2,300 miles. Now, in visible light, then divide the 2,300 miles by the 100 miles, which equals 23. This is 1/23rd. This 1/23rd is a ratio, which is a fraction of the distance. You will not see the difference. It will end at a vantage point. It will end at a vantage point. The horizon will rise with the eye level because of the plane of inclination. And this cannot be done on a ball earth. These are a few ratios of altitude to distances this is a few ratios coming up of altitude to distance of the horizon. Now, the horizon distance to height altitude ratios approximations only. Divide the distance to the horizon by the height or altitude. Divide the feet into feet and miles into miles. Turn miles into feet, then divide. Example, 500 miles equals 2.6 million feet. Now divide. 2.6 million feet divided by 30,000 feet equals 88. So it's 1/88th as a fraction. Or divide miles into miles. Example, 2,300 miles divided by 100 miles equals 23. So it's 1/23rd as a fraction. At the perspective vantage point, the height stays parallel to the ground. Your line of sight stays parallel to the ground, but it is a fraction of the distance of the horizon, and this fractional difference cannot be made out by the eyes. And there's also a plane of inclination, and it seems and it's as though the horizon is rising with the eye level. This creates a vantage point. Now let's go to paragraph 11. It's not the physical plane that's moved, no, but the expansion of your view that's broader. There are three ways to bring an object back into view. 1, physically bring the object toward oneself. 2, use visual aids such as binoculars, cameras, telescopes. 3, go higher. This is why the sun cannot be brought back into view once it goes over the perceptual and perspective limits, once seemingly setting, because of height or altitude above ground, of eye, camera, or telescope, which produces limits at each point of height. The same principle applies to balloon horizons at 20 miles altitudes, rocket horizons from 20 miles to 244 miles up. Everything else is lies to hurt you. This cannot be done on a sphere. This cannot be done on a sphere. Now, look at the altitude to distance of horizon ratio fractions, approximations only. Now, we'll do number 1. At 6 feet, you're 6 feet tall, you're standing at the beach, the horizon is 2.5 to about 3 miles away. So 3 times 5280, which is 1 mile in feet, equals 15,840 feet, divided by 6 feet, equals 2,640, or a fraction of 1/226/40th. Now, you cannot differentiate, your eyes cannot see this small fraction above even though you are standing parallel to the surface, your eyes cannot differentiate 1/26/40th of that of the horizon distance. Now let's try 2. 50 miles equals about 1,000 miles to the horizon, equals 1/20th. 3, 10,000 feet equals 126 miles to the horizon, equals 665,280 feet divided by 10,000 feet equals about 126. Your eye cannot differentiate that. Stop the video at any point to come back and write down these and look at these ratio, altitude to distance of horizon ratio fractions. Come back and look at them. Now let's go to paragraph 12. After researching, photos of Earth over 75 miles are prohibited on the web, internet that is, and in books and everywhere else. You enter a world of falsehoods, of CGIs, computer-generated images, composite image collages, utterly muddied images of indiscernible Earth surfaces, false mathematics, different size curved and colored Earths at same distance, etc., totally and purposely to keep the lie of a spinning ball Earth multi-billion-dollar propaganda brainwash system in place, a culture built on lies, cons, deceptions, corruptions, injustice, exploitation of the hundreds of almost mindless, uneducated millions for political, economic power and money, a billion enslaved minds, unable to see the mechanism arguing unknowingly for their own enslavement. Let's go to paragraph 13. On a ball Earth, 100 miles altitude, the physical farthest one can see is to the tangent points to the surface, about 1,100 miles distance. Even with infrared, it is impossible to see any further on a ball Earth at 100 miles altitude. At 100 miles above a flat surface, the horizon is 2,300 miles to 2,350 miles in visible light and about 4,300 to 4,700 miles in infrared light at about 950 nanometers, which means the same object on a ball Earth are below the tangent point at about 450 miles elevation drop below the line of sight. Now, let me show you this. This is high altitude balloon pictures of the Earth. This is 98,000 to 110,000 feet above the Earth. This is an air horizon. This light blue is an air horizon. This one here is 105,000 feet above the Earth's surface. In other words, 20 miles. This here's the camera lens, approximately where the camera lens is. Approximately where the camera lens is. As you can see, the horizon, this one here is looking straight 90 degrees above the surface. Straight 90 degrees above the surface. Why? Because you have approximately 50% the sky and 50 above the horizon, 50% the sky, and below the horizon, 50% of the Earth. The horizon rises with the eye. How do I know? Because the camera don't have a brain. The camera only sees what it sees, and the horizon rises with the camera lens. This one here is 100,000 feet above sea level. 100,000 feet above sea level. 100,000 feet. Here's the horizon. Here's the horizon. Approximately 50 feet, approximately 50% sky, approximately 50% Earth. Above the horizon, below the horizon. That means the horizon rises with the camera level and the eye level. Once again, here's another one at 104,000 feet. Here's where the camera lens is most likely at, right here. And you can see the horizon. The air horizon is up here. The air horizon is up here. You can see it just tentatively. And down below it is the Earth, and above it is the sky at 104,000 feet. Look at this one. Once again, the camera lens is approximately here. 50% below the horizon, 50% above the horizon, approximately, at 98,000 to 110,000 feet. Here it is once again, 105,000 feet above the Earth. All you can see is the horizon. Approximately 50% of the sky, approximately 50% of the Earth. Now, to continue. Now, the reason the horizon seems to rise with the reason the horizon rises with the eye level on a flat plane is because of, number one, the flat plane never curves downward away from view as one gains altitude. Number two, the altitude to the distance to the horizon is a ratio fraction, producing a perspective vantage point. Number three, the flat plane at 90 degrees to the height line of your line of sight are indefinitely extended, parallel. Number four, the human eyes cannot detect the small ratio difference between the horizon distance and the height above it when they meet at a vantage point. Number 5, the triangulation, a triangulation of the surface meeting your eyes at your altitude point because of expanded view, made by the plane of inclination. Let's look at this once again, the seeming plane of inclination, right here, these dotted lines. Seeming plane of inclination, you're 100 miles above the surface. This is infrared light. In infrared light, you can see about 4,300 to 4,700 miles if you're 100 miles above a flat Earth. The visible light, you can see about 2,350 miles. And this is basic trigonometry. As you can see, the dotted line for the infrared and this line right here makes a triangle. This one also would make a triangle also. This is basic trigonometry. This here is basic geometry. You're 90 degrees to the altitude line. This is 90 degrees to the altitude line here. You're 100 miles above the Earth. You must look down. You must look down to see the surface and the horizon and the atmosphere and all the rest of it. Here's your chord line. Here's your parallel lines to the chord line. 90 degrees. You can only see at 100 miles up about 1,100 miles to the horizon, of which is impossible to see beyond because the Earth is curving away from you. And between the parallel lines, you draw a circle, and that means 1,100 miles. 1,100 mile radius is all you can see as a visibility limit. As a visibility limit. Now, this represents the Earth. This giant circle, this large circle represents the around Earth. This represents these two parallel lines right here, sticking out. These two parallel lines represents a flat Earth. This is 100 miles above the surface. 100 miles above the surface. It is above a sphere and a flat plane both. On a ball, you can see only as far as about 1,100 miles right here to the tangent. To see the horizon at maximum. Impossible to see beyond it. On a flat Earth, it's about 2,300 miles. On a flat Earth, it's about 2,300 miles in visible light. In visible light, and about 4,300 to 4,700 in infrared light. At 100 miles altitude, the elevation drop, on a ball Earth, the elevation drop is about 650 miles at 2,300 miles. Here's 2,300 miles. You draw a line down here, crossing the ball, and 650 miles elevation drop is here. At 100 miles altitude, the elevation drop is about 220. Here's the chord line. Here's the bulge above the chord line, and here's the line here. And that is where this dot is. That's 220 miles elevation drop. On a flat Earth, there is no elevation drop, 0%, because the ground is parallel to 90 degrees to the altitude line of your line of sight. At 4,700 miles distance to the horizon, it's about here. It's about here. It's below the radius line. Now, on YouTube, go to YouTube. Go to YouTube. What you're looking for is no GoPro cameras and no fisheye lens. That's what you're looking for. No GoPro cameras and no fisheye lens, for the simple reason is that GoPro cameras and fisheye lens cameras horribly distort the images. Number 1, top 5 amateur rockets that worked. 2, 60 miles up. NASA shows flat horizon 317,000 feet up. 3, flat Earth Manchester to Orlando 747 flight. 4, no curvature, flat Earth altitude, flat horizon, Eric Dubé, Eddie Bravo. 5, zero curvature, 92,500 feet. to 121,000 feet. No fisheye lens. Flat Earth. 6. Mount Jacinto visible from 120 miles away. Flat Earth. Infrared 950 nanometers. Number 7. 500 miles infrared flat Earth visibility at 31,000 feet. 8. Flat Earth 36 kilometers high. That's about 22 miles. 9. 21 miles up the Earth is still flat. High altitude footage of Earth. Number 10. High altitude balloon 30 kilometers above Earth. That's about 19 miles, 30 kilometers. Now, please go to Google or Yahoo for these keywords. Simply stop the video at any time and go to these keywords, write them down if you need to, and go to them and look at what I've already seen. Yep. Now, cameras that are purposely used to distort the image, part of the lie that Earth is ball-shaped. You must be alert to these camera types. 1. Fisheye lens cameras. 2. GoPro cameras. 3. All cameras that don't show what the human eye sees. I want to thank everyone for listening and watching, and have a very, very fine day. Please share this video. We'll see each other next time.